Okay, for those who want to actually simulate the powered simplest walking using the push-up, here are the slides. Okay, so this pretty much is similar to the simplest bipedal walking using the inverted pendulum because you are only provide the push-up for the double support phase. Your single support phase equations of motion doesn't change, and you can just take the integral over the collision event up to the collision event. The only change is for the collision equation. So you have additional push-up impulse applied. You should formulate this. You should take that into account for the formulation. So previously, remember, when you want to relationship between the after collision and before collision, you apply the angular momentum conservation with respect to point C, right? But since you have a push-up impulse applied, angular momentum is not conserved anymore. You should add up those push-up impulse applied for your impulse momentum relationship. So instead of having hc equals to hc plus, you should add those impulse by the push-up p, which is 2L sine theta and P sine theta. So I just multiply by the LCO cross product P. Okay? And if you just further extend your formulation, you can actually make these two equations equal so that you can find the formulation, which is pretty much similar to the previous one, your after collision effect and the before collision effect, and the additional term by the external angular impulse, which is formulated this way. So you can use this formulation to simulate the push-up powered simplest walking. There are errors here. I should add a momentum here, but I'm pretty sure you could figure that out. This one is right. Okay, so another thing I'd like to introduce is, okay, now coming back to the original issue that I brought up. So there are walking assistive devices providing the actuation or the assistance for the hip joint torques and the assistance for the ankle push-up. Mechanical work point of view, this one is more efficient. Okay, so since the humans walking strategies are using the push-up collision compensation right before the not human, sorry. It's a very simple analysis shows that that's mechanically more efficient. So we would see this assistant devices in terms of that point of view. Okay. Okay, there are studies showing using those concepts to develop the ankle prosthesis. So this is work by Steve Collins and Art Crow. So they provided a passive foot prosthesis that provide the ankle push-up right before collision occurs. So that's okay. So this is a strategy. So what plates are providing the resistive support forces, and there are spring here. So it stores the energy during the heel strike and provide it like a push-up, right, before collision occurs. So this is the passive structure, and the details of the structures are well explained in this paper. So for those who are interested in, I strongly recommend you to search for the article, read for the article. So it's sensors are sensing the gate base, and then there's a clutch motors so that it'll make the energy stored in the spring in the beginning phase of the gate base and then release it when it reaches the push-up. Okay, so you have a heel contact, energy captured and stored, and when the push-up begins, it's been released. Those stored energies will be released, and the energies are provided to the subject. So by mimicking the mechanically more efficient walking strategy, they propose this prosthesis, and compared to the conventional prosthesis, their system reduced the metabolic cost a lot, like 9%. So that's huge. Okay, so this is kind of a fun paper to read if you're interested. Thank you for listening.